In this lesson, we're going to be adding to the function rules that we know derivatives for. We'll be looking at trig functions, sine, cosine, secant, and tangent. We could find the derivatives of the two remaining trig functions, cosecant and cotangent, by knowing those four. As a review, just kind of thinking back through the derivative rules we have so far, we know that the derivative of a constant is 0, so the derivative of y equals 5 or 7 or 11, if it's just a constant by itself, its derivative is 0. The derivative of a power function, we bring the power down, subtract 1 off the power. We have several operational rules now. If we have a numerical coefficient times the function, the coefficient just comes along in the derivative and we find the derivative of the function. If we have two functions added or subtracted, we can just find the derivative of each one. Then yesterday we learned product rule and quotient rule. So if I'm multiplying two functions, the derivative of f times g is f prime g plus fg prime. The derivative of f divided by g is f prime g minus fg prime over g squared. Okay, let's move on to finding the derivatives of sine and cosine. From your lab, you've already seen these derivatives. I expect that you've probably guessed what their derivatives are. So if y is sine x, so sine x is the blue graph, I can see the red graph, that's the derivative. So the derivative graph is cosine x. If y is cosine x, so again, the graph of cosine in blue, and the graph of its derivative in red, I can see that the derivative graph there is related to sine x, but not exactly equal to it. And in fact, since it starts at 0, it's related to sine, but then it goes to -1 instead of going up to +1. So the derivative of cosine is negative sine x. Before we move on from this, let's review a little bit of what we already should know about trig functions, just some trig function basics. We already know that cosine of an angle, call our angle alpha, is the x value. We know that sine of an angle is the y value. We know that tangent is sine over cosine. We know that cotangent is cosine over sine. The ones that you may have forgotten are the reciprocal functions. So secant is the reciprocal of cosine. So secant is defined as 1 over cosine. It's not the inverse, it's the reciprocal. It's 1 over. And then cosecant is the reciprocal of sine. It's important that we know these relationships because that way, if we're asked to work with a unit circle value, then we only have to know sine and cosine. And so if we're asked for secant of an angle, as long as we know the cosine of that angle, we can convert secant to being whatever cosine and find the value. So it's much easier, rather than knowing unit circle values for 6 different functions, just to know unit circle values for sine and cosine, and then if we know those, knowing the rules to convert the other functions to sine and cosine. Make it easier. Also, one of the identities that we need to know, the only one that you actually ever need to know, is this one. Sine squared plus cosine squared is 1. And then making sure that we understand what's being squared there, that translates to sine x, the whole thing squared, plus cosine x, the whole thing squared, equals 1. It matters because written this way, that means we're going to find the sine of x, whatever the sine is, and then square. So our order matters. Cosine first and then square. If we were going to square x first, the square would have to be written beside the x, not beside the words for sine and cosine. So every time we see these squares beside alphabetical labels for functions or verbal labels for functions, we're going to think of it as parentheses and the whole thing squared. We could also find the derivative of y equals tangent x. Since we know that tangent is sine over cosine, we're just going to say, oh, well then y equals tangent means that's the same as y sine x over cosine x. We know the derivatives of sine and cosine, and we know the quotient rule. So if you want to pause for a minute and see if you can work it out for yourself, that would be great. I'm going to go ahead and work it out. So to find the derivative, so then y prime is the derivative of the numerator, the derivative of sine is cosine, times the denominator unchanged, minus the numerator times the derivative of the denominator. The derivative of cosine is negative sine, all over the denominator squared. If I simplify a little bit in the numerator there, cosine x times cosine x makes cosine x squared. Then the negative times the negative, all these are multiplied, so I'm fine to multiply this negative by the negative in there. That makes me positive sine x squared, all over cosine x squared. Then I remember, because I just reviewed it, that cosine squared plus sine squared is just 1 over cosine x squared. And that's one version of the derivative of tangent x. Another way to remember the derivative of tangent x is that 1 over cosine is secant. So 1 over cosine squared would be secant x squared. Or if you're a true mathematician and lazy, secant squared x. Similarly, we could find the derivative of secant x. I'm not going to go through that, but you can if you want. You would rewrite secant as 1 over cosine and then apply the quotient rule. It turns out that if y is secant x, then its derivative is secant x tangent x. We won't derive that one, but you can do that on your own if you'd like. Okay, let's look at some examples. The derivatives involving trig functions. I have to be careful now because I have a whole lot of rules to be paying attention to. So when I look at my first example, I see there are two functions here because I see the independent variable there twice. That's what tells me I have two functions. I see x and then sine x. And I have to think, okay, well, what's the relationship between those two functions, that x and that sine x? They're multiplied. So I have product rule here. This is actually x times sine x. So I want to be careful not to miss that product rule. So I need product rule, and then within product rule, I'm going to be dealing with the derivative of sine. So you can write out your f and g for product rule and do the rule if you'd like. I'm going to do it without writing out because eventually we want to get to the point where we don't have to write out f and g to apply the rule. So the derivative is the derivative of the first term, so the derivative of x is 1, times the second unchanged, times sine x, plus the first x times the derivative of sine is cosine x. And I'm done right there. I can't do anything else. That's as simple as I can make that derivative. So again, my derivative, the derivative rule that I used was f prime g plus f g prime. The derivative of the first, derivative of x is 1, times sine x, the second unchanged, plus the first unchanged x times the derivative of the second, the derivative of sine x is cosine x. And when I look at my next example, I see I have two functions there. I have x there twice. In this case, it's obvious what the relationship is. It's addition, so I can just find the derivative of each one. The derivative of tangent x is secant squared, or 1 over cosine squared, if you like that better, plus, in my second function, the 3 is a coefficient because it's 3 times cosine x. It's not just 3 hanging out there by itself. So 3 is going to come along. The derivative of cosine is negative sine x. And then I could simplify just a little bit by multiplying the 3 and the negative and getting negative 3 sine x. But that's all I can do. I'm done there. And then my last example here, before I get to the tangent line example, is a quotient rule. Again, it's very obvious. I do see the independent variable there twice. I have x twice. I have two functions, but it's clear what the relationship is. It's quotient rule. And I remember that the quotient rule is f prime g minus f g prime over g squared. So that's the rule I'm going to use to find the derivative. I'm not going to write it all out. I'm just going to try to do it mentally. So the derivative of the numerator, the derivative of cosine x, is negative sine x times the denominator unchanged minus the numerator unchanged times the derivative of the denominator all over the denominator squared. And I can leave it like that. It's fine if you want to. You could clean it up a little bit, make it look a little nicer if you wanted. Negative x squared sine x minus 2x cosine x all over x to the fourth. And then if you wanted to be really fancy, you could factor out and cancel an x. I'm going to leave it there so I have enough space to do my tangent line equation. Okay, and then number 4 is our ever-present equation of the tangent line. Find the equation of the line tangent to, there's my function and there's my x value. It's the way they're typically presented. Anytime I see equation of the line, I'm going to think, okay, I need slope and I need a point. I've been given half the point, 0. Sometimes I'm given the other half, but not anything else. I'm going to find the rest of the point first, and then I'll go back and find the slope. So to find the y value here, I know that y equals x plus cosine x. If x is 0, that's 0 plus cosine of 0. Cosine of 0 is 1 plus 0 is 1. Then I have to find my slope. The slope of a line tangent, the slope of the tangent line is the derivative at x is 0. So I need to then find my derivative. Let's see, I'm going to do that just right under here. So y prime, the derivative, I have two functions here, x, cosine x, see that x twice. The relationship is clear, they're being added. I can just find the derivative of each part. The derivative of x is 1. The derivative of cosine x is negative sine x. Then I need the slope when x is 0. So y prime of 0 is 1 minus sine of 0. The sine of 0 is 0, so I end up with 1. Lots of zeros and ones wandering around in the screen. So then my tangent line now I'm ready to actually write the equation of the line. I have my slope, I have my point, ready to write it. Y minus the y value of the point is equal to the slope times x minus the x value. I could simplify that a little bit. Y equals x plus 1. I could graph that to check. X plus cosine x looks like this. So I could graph to see if y equals x plus 1. And it is, in fact, if I were to graph it, I would see that, in fact, it is tangent to the graph there. So remember, that's visually what I'm looking for. The graph of x plus cosine x is wiggly. I'm looking for the graph of the equation of a tangent line to that wiggly graph at the point where x is 0. Okay, that's it for today.